So a while ago, we saw that given a random variable x, which was log normally distributed, we could convert it into a random variable y, which was Gaussian or normal distributed by simply taking the natural logarithm operator, right? So given the values of x1, x2, so on, so forth, xn here, if I just applied log of x1 or natural logarithm of x1, natural logarithm of x2, natural logarithm of x3, so on, so forth, I would get my y1, y2, y3, so on values, and all these yi values are Gaussian distributed. This was very useful, right? Because as soon as I know that my values are Gaussian distributed, I can put all the machinery of Gaussian distribution. And again, I have all the machinery of Gaussian distribution at my disposal to understand, to analyze my data much better. Because Gaussian is extensively studied, and even in machine learning, we make Gaussian assumption a lot of times. Trust me, we assume a lot of times that a variable or a feature, or a variable is Gaussian distributed. We make this assumption, otherwise the math may not work in all the cases. So given some random variable which has log normal distribution, it was very easy for us to convert to Gaussian distribution, and then we can use the fact that the variable is Gaussian distributed a lot in the whole of machine learning. Now the next immediate question, again, I'll come back to this when we discuss machine learning algorithm. I'll keep referring to this, that we have made a fundamental assumption that a feature or a variable is Gaussian distributed. Now the question here is, given a random variable x, which is Pareto or power law distributed, is there some way for me to convert into a random variable y, which is Gaussian distributed? So is there some way to do it? Because this is very useful, right? Because you notice Pareto distributions and power law distributions a lot. Okay, so I would use the words power law distributed and Pareto distributed interchangeably. You notice this a lot in nature. Now if I can convert this into Gaussian, life is very good. Now how do we do it? So we can do it using something called a power transform. And one such very popular power transform is called Box-Cox transform, named after two mathematicians. Okay, I'll explain you what is Box-Cox transform now. Okay, let's assume I have a random variable x with values x1, x2, so on, so forth, xn. And let's assume x follows a Pareto distribution. Okay, and let's assume I have a random variable y, which is y1, y2, yn. Okay, and this has to be Gaussian distributed. Okay, now I want to convert, I want this conversion. I want a way to convert my xi's into yi's. Now let's see how to do it. So as soon as you call the function Box-Cox and give it your xi's, your vector x, okay, let me call this vector x or observations. As soon as you give it vector x, all these n observations, it will return you a value called an alpha. Okay, this is so let's see, we'll use this alpha. Okay, I'm writing the steps. As soon as you call your function Box-Cox, it does some very interesting mathematics internally, which is beyond the scope of this course. But as soon as you give it observations, so you're giving n observations here, right? x1, x2, so on. As soon as you give n observations, it returns your value called alpha. Now, as soon as you get your value of alpha, you can generate yi as xi power alpha minus, sorry, it's often called as lambda, not alpha. Sorry, my bad, my mistake, sorry. It's often called as lambda. Okay, so sorry, my bad. I just got a little confused with two things. So xi power lambda minus 1 by lambda. If your lambda is not equals to 0, it is log of xi if lambda equals to 0. Now let's see what it means. Okay, this is very interesting. So given each of my xi values, for all I goes from 1 to n, right? So let's go into the details of it. I'm given n values of x, okay, and using Box-Cox, by just using Box-Cox of x, I got a value called lambda. Okay, using this lambda now, I'll convert each of my xi's into yi's using this formula. Now the question is, how did we come to this lambda? That is beyond the scope of this class. So how is lambda computed is beyond the scope of this course. It's slightly mathematically intense, so I'll skip it. For those of you who are interested, Wikipedia has very good links on very good references on how this lambda is to be computed. It's a fairly People who are coming from mathematics and physics backgrounds will be able to understand some of this. If you're a classical computer science guy, we don't learn sufficient amount of math for this. Okay, so now we know how to convert each of my xi's to yi's. Now there is this boundary case here. If it returns a lambda which is equals to 0, okay, what we are doing is basically a natural logarithm. This is natural logarithm, right? So what is natural logarithm? So if lambda equals to 0, what it means is that xi is log normal, that x is log normal, right? Because if it's log normal, if I take the natural logarithm of it, I'll get a Gaussian random variable, right? So these are Gaussian distributed. My yi's are Gaussian distributed. So whenever lambda equals to 0, you're just basically taking the natural logarithm of xi's, which implies that whenever lambda equals to 0, your random variable x is log normal. Else, you just apply the simple transform. This is a very, very elegant way for you to convert so this is a brilliant way for you to convert any Pareto distribution to Gaussian distribution. Now, let's go through some simple code on SciPy. Okay, so your SciPy, as you know, has brilliant statistics toolbox or library. So in statistics module of SciPy, you have a function called boxcox. Okay, it takes an n-dimensional array. You can just give it an array of all values. If you already know the lambda, you can give it, or else you can just leave it. It will compute the optimal lambda. Okay, alpha, we don't have to worry too much about it right now. Okay, what it returns you is, it returns you an array of transformed boxcox array. So what it returns you is boxcox power transformed answer. So if you just call this function, if you just call this function like this, if you just say boxcox of x, it will give you y, where it has computed the alpha. By doing this, it first computes your, not alpha, I keep getting confused with this, I'm extremely sorry. It computes the lambda and uses the transformation that we saw here. It computes this transformation that we saw here and obtains your y's. It does all of this in literally one line of code. Okay, now let's see some sample code on what it is. Okay, thankfully, SciPy documentation is really, really good. Okay, so let's see what I'm doing here. Okay, so I'm basically importing stats, I'm importing some plotting tools, and here I'm creating a random variable from a distribution called log gamma, which is one of the power law distributions. Okay, so this is not normal, this is log gamma distribution. Gamma distribution is one of the interesting distributions in statistics that is not extensively used in machine learning, but in this case, let's just go with the example. Okay, this is one of the Pareto distributions or one of the power law distributions here. Okay, and we are creating we are creating 500 samples, right? And what we're trying to do here is we are doing a stats.prop plot. This is nothing but your QQ plot, right? So I'm trying to do a QQ plot between a variable x, which is log gamma, okay, and y, which is normal. Okay, so let's see what is the outcome of this. That's the first plot that I'm trying to draw. Sorry. Okay, so in this plot, my x-axis here is normal. Okay, and my y-axis here are my log gamma distributed random variables. As you will quickly notice, there are a lot of points which are deviating, and these are just 500 points here. Okay, we generated only 500 points. As you'll see, there is a lot of deviation here, and the deviation here is also getting worse and worse. So by just looking at this probability plot or QQ plot, you can easily say that your random variables y and x, so this is your y and this is your x, are not coming from the same distribution because there is significant deviation from the straight line in your QQ plot. Now let's do the trick. Now let's do the interesting trick. Now what I'll do here is I take my values of x and I pass them through stats.boxcox. And I take these values into xt. Now xt is like my y. Okay, so I've input x and I've output y. My x I know is log gamma distributed, which is one of the power law distributions. Okay, my xt, if power boxcox worked perfectly, my xt would be Gaussian distributed, right? But how do we verify this is Gaussian distribution or not? We just use the probability plot or the QQ plot after boxcox transformation with xt and normal distribution. Now, as you will quickly notice here, this plot, here we have normal distribution, the theoretical normal distribution. Here we have xt, which is Box-Cox of x, right? Now we will see that most of these points lie very, very close to this straight line. So from this you can conclude that xt is normally distributed. And how did we get xt? We got xt by doing simply Box-Cox of x, right? So it computed the lambda internally and it did all the transformations to get us our xt. And xt is normally distributed, and we can visually see this using this QQ plot, right? So the function box plot in scikit, in scipy.stats package gives us all of the important stuff on transforming a random variable x, which is power law distributed, to a random variable y, which is Gaussian distributed. So it goes from a Pareto distributed or a power law distributed random variable to a Gaussian distributed random variable very, very easily. It's literally one line of code. That's the beauty that I love with Python. Most of the important functions that we learn in this course and we even apply in the real world can all be found with one-line code snippets.